guys, now let's continue with this Plug Flow Reactor. I'm going to give you a small description of what it is and how it's operated, and then we do a molar balance on it. So the description is essentially, you should know it also as tubular reactors. Why tubular? Because they are tubes or pipes. So this is the typical arrangement. They go like this. You're going to see more photos later. They are cylindrical pipe reactors. They are operated in steady state. Makes sense because you get inside stuff and you get the outlet here. It's often in gas phase reactions, but you can do them also in liquid phase or gas liquid. No, that's not that normal, actually just gas phase, or either gas phase or liquid phase. The reactants are consumed as they pass through. Well, for example, you got A plus B. They start reacting, A plus B goes to C, and as they pass through the pipe, they finish, I don't know, maybe a lot of C and not that much of A and B. The reactants are consumed, yeah, that's true. It's the simplest form of a reactor. I tell it because it's literally a pipe. You don't need to do a tank or whatever, it's just a pipe. They mix because of the turbulence, and yeah, essentially that's the thing. So let's continue how it's operated. It's operated with a plug flow. So if you remember, plug flow means it has a lot of turbulence. A lot of turbulence means they are going to mix, and if they mix, that's good because we need A in contact with B so they can form C. That's an example. So there's no radial variation throughout the pipe, so if you will have this diameter here, you will suppose that the concentration throughout the levels, even though it's near or away from the center, is the same. Also, that's kind of ideal, but okay, we need to start with something, guys. The pipe incrustation may happen, so there is a maintenance program to follow. So yeah, you have it here and it starts getting incrustations here, and eventually it's going to be, I don't know, something very, they start, you need to take it away because then your pipe is going to have corrosion, or worst, your reaction is not going to be carried, or if it is carried, not with the percentage yield you want or conversion. So yes, you need maintenance programs to take care of that. The good thing here is that it's easy and cheap to buy and operate. So yeah, you got this pipe, you need to calculate the diameter, the size, and how much flow do you want to get and how much product you want to get, and you just buy it and operate it. The bad thing, there are no so high conversions such as in batch reactors, but yeah, it's typical in the industry to have this. So one thing I do want to remark is this plug flow stuff. So if you've seen transport phenomena or pipe flow or fluid mechanics, you should remember that this is the typical linear velocity flow. You can see the more near the wall, or the nearest the wall is, the lower velocity, and in the center you got the faster. You could also have a asymmetric distribution, but what we want here is essentially to get a plug flow like this. We want these eddies or these formations here because they are going to mix letter A or B and C, they mix them, and mixture is good for reactions. So that's why we like to have a plug flow reactor. Not only that, we also want to have fast fluids. We don't want slow fluids in pipes. So that's why we're going to pump it and they mix themselves and you take them away. So that's about theory. Now let's do some applications of the general mass balance equation. So let's suppose we have this pipe. I'm going to cut this pipe, and you can see there's an inlet flow here and outlet flow here. Here goes A and here goes product B. Now, as it's you can see here the profile or velocity profile is as a plug. You don't have this beautiful arc which is typical for laminar. We are in turbulent case, so we have this profile. Now if I wanted to cut this little disc, And probably you're asking why I'm cutting this. The problem is that the concentration is changing with length, so I need to account for that. And one thing I've seen before in mathematics is that if you do a analysis in a small infinitesimal part, you can apply it throughout the system. So let's do that. From the mass balance I got, yes, I got an inlet, yes, I got an outlet. Because there's a reaction, I got the generation term, and because it's steady state or a continuous process, there's no accumulation. So this is 0. So essentially we are done with this equation. This is 0, so I send this to here, subtracting, so that's why the minus term. And yeah, we got this equation, and we have two problems. Actually, these are not that much of a problem. The real problem is this one here, because the rate of reaction does actually varies with the length of the, let's say with the reactor. So if the length changes, you know that there is a length and we have a transversional area here, we're going to have volume. So yeah, as volume changes, we are changing the rate of reaction. So for example, a typical rate of reaction law will say that K times the concentration of A. So if we calculate the concentration here and the concentration here, we will have different rate of reaction. So we will have KCA0, and we will have another rate of reaction here, KCA. So as you can see, the point of the reactor is of course change the concentration with length. So the rate of reaction is also going to change with length. So we cannot take this length away. We need to do something with this. So the approach I told you before is let's analyze this differential disk, because what I've learned from mathematics is that everything is beautiful in the differential world. So yeah, we got this disk. Let me explain you a little bit. So this is the tube here. We got this diameter. You don't need it, but of course this diameter. You got this inlet, which is the flow of J evaluated in this volume here, and the flow of J evaluated with this volume plus the change in volume. Where is the change of volume? Of course, this little disk has a change of volume. So we have one volume here, and if we add this little volume here, we will have volume plus the change of volume. And this differential disk has also a change or generation concept. So read this part slowly because it's a very conceptual part, but we are going to be able to form a new concept. So the inlet, this is the inlet. My flow of J evaluated at this certain point. Now, the flow of J at the outlet will be this one. Volume plus the change in volume. Now, RG, which is the generation, is simply times the change in volume. And because it's accumulation, we have since it's continuous, we have no accumulation concepts. So let's reevaluate inlet, outlets, and the generation concept, and we get this thing right here. Well, sorry, this one. And what I'm going to do is essentially divide everything by the change in volume. So this inlet and this outlet are divided by the change in volume. I used to have a change in volume here, but since I divided by the change in volume, I take it away. And I'm going to take away this value, the rate of reaction. I get it here. And if you're good at math, or at least you remember this form, this has a familiar expression of a derivative. So let's force that derivative. What do we need to do is the limit as the change in volume goes to 0. That's the definition of a derivative. So this here will be a differential of flow, and this here will be a differential of volume. That's the rate of reaction. And yes guys, we are done. This is our design equation. If you want to integrate it, you can do it. You just need to change this one here, and since this is dependent on flow, you can change it and you will get something like this. In terms of volume, you get an integral, and remember, we love this is positive RA, but we want negative RA, or rate of reaction here. So we force it. So that's my actual equation, this one here. I like it because you got volume, you got the differential of flow, so that actually depends on how the rate of reaction law is. It can be as simply as one constant, so it will be easy, or it can be as complicated as, I don't know, the flow of A to the square times the concentration of that number to the square root, and yes, this will be kind of complicated to do, but you can do it with numerical methods. And yes, we're done with the PFR. That's the master equation. It's a little bit more complex because you need to know more about this little disk. And yes, hopefully you get the idea of why we did this analysis on the disk and why do we evaluate it at volume and at volume plus change in volume. And if you get that, all the rest is just mathematics. So see you in the next video. We're going to talk about packed bed reactors. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.